Hello friends, this is lecture number 8 on Staad software. Today we are going to see wind load design, earthquake load design, and how to use truss members and use of specifications which we left before. First open Staad software, open a new project. Let's see a truss member. Firstly, name it. Go to structure design. Select a truss model. It has 4 bays longitudinally and 1 bay across the length. Import it in our Staad Pro structure. Now input setup information. Go to geometrical property. Go to front view. Now provide support column to our truss member. Select the our truss member. Go to geometry tab. Select move members. Select bidirection up for 3 meters. Click OK. Click yes. Click yes. Now check for orphan nodes and duplicate members. No duplicate members are found. Similarly, duplicate members. Okay. Now create 6 nodes. Check out the nodal distance, 25 meters. $10. Now generate nodes. Join nodes. Go to Staad editor command. You will select truss member. OK. Now provide the properties to our member. Select section database. Here we have different code section. Select Indian code. ISF section. Go to table. Here we have section details. Select the section. Edit. Similarly, angle sections. Assign it. Now define a properties for column. I can define a I section. Select the member. Edit. Assign it. Now go to support. Create a fixed support. Now load definition. Now define load case detail. Generally the truss member have UDL and point load. So let's define it. The first one is nodal load. Let's take nodal load as 50 kN. Edit. Take a UDL. Let's take it minus 10 kN. Edit. Assign it. Similarly, assign this load. Run analysis. We have 0 errors. Now go to post processing mode. Select dead load. Now in still structure, we can see is our structure fail or pass. Select the ratios, click apply. The green shows our structure are passed and load, click OK. Similarly, we can see all the details. As our member is truss, there is no bending moment in the structure. Now if we create a space frame, our structure will have bending moment also. Now select the beam. Now see, it has bending moment as well as shear force. See, it has bending moment as well as shear force. Close it. Now the use of wind load and earthquake load. Delete our input data. Save it. Now open structure wizard. Input a framed structure of height 15 meter. Length 12 meter. Width 6 meter. Click apply. This is how our frame structure look like. Import it. Now apply property. Define property. Let's define same property to all sections. Now define supports. Sign it. Now the load definition. Here we have different definitions. Vehicle definition, wind definition. Add wind definition. Comment it. Add it. Click add. Now a new window is open, which asks us the pressure intensity at different height. Now before input this data, Let's see how this pressure intensity is generated. For wind load analysis, we can use IS 875 Part 3 1987. This is our structure for which we are going to do wind analysis. The basic data we need in wind analysis is basic wind speed for the region we select our structure. Then we need to calculate design wind speed, which depend on different factors, that is probability factors, terrain height and size factor, topography factors. Select appropriate factor value from our code according to structure. Here we defined our structure for the hilly region, so we take basic wind velocity as 47 meter per second. Similarly, probability factor K1 equal to 1 for 50-year design life. Then terrain category 3 and our structure class A, and topography factor 1 for upwind slope less than 3 degree. So we get our design wind speed as 47 k2 meter per second. Now the next step is pressure intensity or design wind pressure, which is 0.6 Vz square. Now the wind load acting on a structure member due to pressure intensity given by Cf into A into Pa, where Ae is effective area dependent on solidity ratio, which is also known as exposure factor. Cf force coefficient factor, which depend on solidity ratio, effective solidity ratio beta, and frame space ratio. For this structure we take solidity ratio is equal to 0.2, and for flat frame solidity ratio is equal to effective solidity ratio beta, and here we take frame space ratio equal to 1. So the Cf factors comes out to be 0.9, which was calculated from IS 875 part 3 code. So the final input data we need to feed in our design part is exposure factor which is 0.02 for our structure, force factor 0.9. Similarly, pressure intensities are calculated for different height. We find out the value of K2 from table 2. Similarly, the pressure intensities are being calculated. Now let's input this data in our design. Input the data. For intermediate height, the pressure intensity gets interpolated. Click add button to add it. Now here is exposure factor which we defined, that's 0.2. Add it. Apply it to our whole structure. Now define load case. Find outer load combinations. Edit. Now define dead load. Assign it. Similarly, assign this property. Assign to selected beam. Now define wind load. Go to wind load definition. Select type 1. Wind load acting x direction. Now force vector 0.9. Applying range minimum 0, maximum structure open or close. Edit. Similarly for z direction. Edit. Now you can see the pressure intensity is applying on frames of the structure. Now click analysis. Add analysis. Run analysis. Click whole structure. Now define floor load. Similarly for live load. Run analysis. Clear 0 error 1 warning. Click done. Now you can see the shear force bending moment. Go to post processing. Select the load cases. Click apply. Now go to front view. Click the reactions. Similarly the animation, section displacement. Click apply. Select the load cases. For different load cases we have different response. Now add a earthquake load in our structure. Again go to load definition. Define seismic definition. Edit. Select Indian code. Click generate. As you can see, is similar to wind load, there are different factors K1, K2, K3. Here also we have different factors. For seismic definition, define them according to the city, according to our structure, that is zone factor. Then according to our structure, response reduction factor. Then importance factor, general building or important building. Then type of soil, type of structure, dampness ratio of our structure if we have no. Then period in X and period in Z, we can define them. Click generate to generate it. Click add. Now the next one is self-add. In earthquake load, the dead load is added 100%, but live load is added either 25% or 50% according to our structure. Right now we are adding dead load 100% and live load is 25% of our structure. So self-add is dead load. Then member weight, UDL. The dead load has minus 7.2 kilonewton per meter. UDL. Edit. Element weight. Floor intensity. Minus 3.75 for dead load. Edit in variance. Minus 0.75, that is 25% of 3 kilonewton per meter square for live load. Edit, close it. The self weight is automatically assigned to our structure. Assign UDL. The floor weight is automatically assigned. Now define load case. Earthquake in X direction. Edit. Similarly, earthquake in Z direction. Edit. Define them. Go to seismic load definition. Define factor 1. Edit. Similarly, for Z direction. Edit. Now if we run analysis, we see one error was there. What was the error? That is, earthquake load should be defined firstly. If we define this load later, it can't be analyzed by the software. So we have to assign this load first. So the best way to do this is go to stat editor, change the level, delete the auto load combination, we will generate it again, save the structure. Now you can see here again arrange them sequentially. Save it. Now generate auto load combination. Total 17 cases are generated here. Click add, run analysis. We have 0 error, 2 warnings. Go to post processing. Now here we can see the support reaction. Go to the remote, support reaction, force y direction, absolute value. Now here we can see the maximum support is on node 6. As we select the node from table, the node is highlighted. Node 34. Now beam, bending moment, shear force diagram. We can check out any beam, bending moment, shear force diagram from here. The deflection, the animation, section displacement. Now this is animation for dead load. This is for earthquake in X direction, for earthquake in Z direction. Similarly for different load cases and load combination. Now we can generate our report file from input output data in the picture summary. So here we have generated our output file. So this is all for today. In next lecture, that is last lecture, we see a workout example using all the tools and load combinations we studied till now. Thank you.